Yep. So hi, I'm Richard. I'm a postdoc at King's. I work on developing MONAI core and also more recently MONAI stream that we'll chat about in a little bit. And so in this session, I'm going to talk a little bit about invertible transforms. So if can you see my screen okay?
Yeah, we can see it.
Great. Okay, thanks. So if you go to the Bootcamp repository for today, and if you go into day 2, it's been updated and there should now be a notebook on inverse transforms. And so we're going to work through that. It's mostly sort of a click and play thing. There's no real opportunity for, there's no really questions or moments where you have to fill things in. And that's because for the most part, the inverse transforms should just work. They should just do what you hope they would do. And so there shouldn't be too much need for creativity, I would hope. But so we're going to run through it, and feel free to ask any questions if there's anything that needs more clarification. So yesterday, Eric started talking about transformations and how we can use them, obviously, to transform our data. So the first one in our chain of transforms is typically the loading of an image, say from file. And then after that, we want to do some sort of pre-processing of our data. Maybe our image is, our voxel sizes are too small that we can't really feasibly do segmentation on that. So we might do some downsampling, do our segmentation, those sorts of things. So there's the sort of the data processing that goes into it. And then, as I'm sure you all know, there's then the data augmentations, which we'll typically apply. And this can help increase the variability in our data. And so if we have a limited data set, it can help reduce overfitting of our model. But then once we've applied our transforms and say we're working on segmentation, it can sometimes be useful to then do the inverse of those transformations. And that can be useful, say, if you want to take your image that's saved on a file, let's say it's a nifty, do some pre-processing, put that through our model, get out a segmentation. And then if we do the inverse, we will then get it back in the original space of our input file. And so if we save that then to file, we could then, using an external viewer, anything like ITK Snap or Slicer or whatever your preferred viewer is, but outside of sort of a Python, just using a matplotlib viewer, you could then view them and they should hopefully superpose quite nicely with each other. So that's one of the main motivations for doing inverse transforms. If you can also do inverse transforms, you can do things like test time augmentations, and we'll chat about those further down the notebook when we actually get to using them. So if we just jump straight into the notebook, we've got all of the same sort of things that we were seeing yesterday. So this one says, if MONAI is not installed, please install it. We've got a lot of the normal imports here because we're working on transforms. There's quite a lot of imports for our transforms, but really nothing that you won't have seen before. So that's everything so far. In the next cell, we've got something really simple just for helping visualize our images. And so it's just going to do a subplot. The only thing here is I've changed the ratio of each of the subplots so that if an image is bigger, the subplot will then be bigger. So that should just hopefully help us visualize some of our data as we put it through different transforms. Great. And then throughout the whole of this notebook, I'm just going to use really simple 2D data. It's the circles that Eric was also using yesterday. And so it's 2D, but needless to say that everything we are doing today would work with 3D data, and of course it would work with real data as much as the circles. Everything should be exactly the same. So here you can just see an example of one of these sort of data that we're going to be working with in this notebook. It's an image that's 100 by 101. It's got a single channel dimension to it, a singleton, and I've just set the segmentation to be everything that's non-zero. So later on in this notebook, we're going to do a tiny bit of learning, but you can see that it's a trivial, easy task. So the segmentation is just everything that's non-zero in our input image. Great. So you might be asking yourselves, which of the transforms in MONAI are invertible? And that's something that you can easily find out because all of our invertible transforms inherit from a class called invertible transform. So, so if you execute this cell, you'll see that rand rotate, the dictionary form, sorry if this is quite small, the dictionary form is invertible, but the array version isn't. Now, the reason for that, and I explain a little bit above, feel free to read through at your own pace. The reason for that is to do the inverse of the transformation, you need to store certain bits of information. So for example, if we're going to randomly apply a rotation, we need to then know what that rotation matrix was to then be able to do the inverse of it. And you should hopefully remember that when we use our dictionary transforms, we can then have some extra information. So we might put our image into the load image transform, and at the end we'll have not only image as an output key, but we'll also have image meta dict, and that will have all of the metadata that was associated with that image when we read it in. And but in the same token here, we're going to return the image, but we're also going to create an extra key, and that's going to contain the information that we're then going to need to be able to do the inverse of that. So all of that to say, if you're interested in doing inverse transformations, stick to using the dictionary versions of our transformations as opposed to the array versions of our transformations. And then inside of the dictionary transformations, the majority of our spatial ones are invertible, but feel free to just check the ones that you're interested in using and check that those are invertible. I think the two which aren't, that could be really, are our random deformation ones. So our rand, I think it's called rand elastic 2D and rand elastic 3D. And these could be inverted, but we just haven't put it high enough on a priority list right now. But aside from that, pretty much all of our spatial ones and a fair few of our intensity ones are invertible. So here in this next cell, you can see that the transform is a single transform, and it's the rand rotate. And so, as I say, we're going to use the dictionary form. We're going to rotate it over some range with a probability of 1. And I've said to keep size to be false, and so that means that as it does the rotation, the image is going to grow in size so that you don't lose anything. So get some data, apply the transformation, and the transform data is under this variable name. And you can see that it's really simple. All we've done is rotate this image, and we've got the output here. And obviously the image and the segmentation match each other beforehand, and they match each other afterwards because we've used the dictionary transformation. Here, though, you can see this is what I was talking about, how when we're using our dictionary transforms, we can save extra information. So beforehand, our dictionary contained just 2 keys, one being image and the other one being label. And then after having applied the transformation, we have an extra 2 keys, one for image transforms and one for label transforms. And if we look at what the just one of those transforms is, you can see that it's a list, and this list contains one element, and that's because we've only applied one transformation. And so if we applied multiple, there would be multiple elements to this list, and the first element is the rand rotate. It tells us what the original size of the image was. It tells us what the random rotation matrix was, tells us the type of interpolation that we used, all these sorts of things. It also tells us that because it was random, there's a probability that it would have been applied, and there was a probability that it wouldn't have been applied, and it's telling us that this time this random transformation was applied. So again, hopefully you won't really need to be concerned about any of this sort of things, but it's just so that you're aware of the information that's then used to compute the inverse transformation. So that's it. So take some image, apply some sort of transformation, and you'll see that there's some extra information that's then contained in our dictionary. Here, all I'm doing is I'm just stepping up one tiny level in complexity. Instead of using one transform, I'm now using 2 transforms, and I'm using them in a compose. Both of these are the dictionary transforms, and both of them are invertible, so that when we apply the transformation, first we're going to do some sort of random rotation. And then afterwards, we've cropped it tight around. So that's what the crop foreground transformation does. And so now you can see that in our list of image transforms, we now have two elements, the first one being the random rotate. So that's similar to in the previous cell. And now we've got an extra one, which is the crop foreground. So hopefully you can see that when we do the inverse transformation, we'll want to do the inverse in the reverse order. First, we'll want to undo the crop. And then after that, we'll want to undo the random rotation. It's worth noting that some transformations are going to be lossless and some transformations are going to be lossy. And by the same token, the inverse could be lossless or lossy. For example, in the rotation, there's going to be some sort of interpolation. And so that's a lossy transformation. And so the inverse is going to be double lossy. You'll lose some information when you do the forward transformation, and then you'll use that to do the inverse transformation. So you'll lose extra information. Other ones, like the crop foreground, if all you ever remove from the crop foreground is 0 values, then when you pad those 0 values back in, that's a lossless inverse transformation. So there's no way in MONAI of asking which ones are lossy versus lossless. But I think if you think about it, you should be able to reason to yourself which ones may or may not be lossy. Essentially, if it involves the loss of data because, say, you've cropped information out, or if there's some sort of interpolation, then it's going to be lossy. Great. So all we did there was we added in an extra transformation to crop it. And then in the next cell, we're going to do the inverse. So all of our invertible transforms contain the method called inverse. Compose, because compose could contain invertible transforms, also inherits from an invertible transform. And so if we do the inverse of that, we save that in a new variable called data inv, and then we visualize that, hopefully everything should go back to how it was to begin with. So we're going to visualize the original image, the image that was put through the forward transformation, and then the forward image that was then put through the inverse transformation. So hopefully it should come back to where it was. So that's the image, that's the forward transformation, that's the inverse transformation. So hopefully you can see that it lines up with the original. And then here you can see that we've just taken the difference between the two of them. And again, the rotation is lossy. And so that's why it's not, the difference isn't perfectly 0. But to all intents and purposes, it looks pretty good. I mean, here you can see that it's slightly more blurred compared to the original. Great. So that's all well and good, but really all we've done is taken an image, applied a forward, and then applied the inverse to that. In reality, what we'd probably like to do is we'd like to take an image, apply a transformation to it, run it through our model, and then put the inverse on the output of our model. And so to that end, we're just going to do a really simple bit of training. And all we're going to do is we're going to try and segment that binary task. So it's a really, really, really simple training task. So we've got some transforms. We're going to use our random rotate. We're going to randomly flip our image with a probability of 0.5. We'll do some scale intensity. And then at the end, we're going to make sure our image is divisible by a factor 16. Our data is just going to be 100 instances of those random circles. And then we create a data set and a data loader. This is all very, very vanilla. Our UNet is a tiny, tiny UNet because it's such a simple task. We've got a massive learning rate because it's such an easy task. Anyway, I'll just execute this and it should only take a second, I hope. And then once it's done, we'll check what the results of that segmentation were. Great. And so here I've just created a tiny little function to sort of like a helper function to help us do some sort of test inference. And so we're going to get some fresh data, apply a forward transform to it, and do our inference, where the inference is take our image, put it onto our device, add in the batch, put it through our model. So this is going to be our inferred image. We're going to save it under some key, which by default is infer. And then we're going to apply some post transforms to it. And we're going to do that again on that data. And then the hashable is going to be infer. So we're going to apply our sigmoid activation, and then we're going to ask for it to be discrete. So that's it. That's just how we're going to visualize our data. So here's our input image, here's our input segmentation, our ground truth segmentation, here's our transform image and our transform segmentation, and this is our inferred image. And so it was such a simple task, naturally you'd expect these two to look pretty similar. So now the question is, how can we do the inverse of our segmentation, our inferred segmentation, so that it lines up nicely with our original input image? And to do that, I've taken the cell from above, and all I've done is I've added in this extra post processing transform. So earlier, our post transforms were activation as discrete, and now we're just saying, I also want you to do the inverse. So this is the invert dictionary transform. It's going to apply on our out key, which as we know is infer. Well, by default is infer, but we want to use the images transforms. So because we took our image, we applied some forward transformations to it, we then get out something which we're going to save under the key, out key, and then we want to apply the inverse to out key based on the forward of the image key. Hopefully that makes sense. And all of that to say, you take your image and your segmentation, you apply your forward transformations to it, you do your inference, and then you just do the inverse of that. And hopefully you can see that this last column looks very similar to our second column. So we've just put it back into its original space. And as I say, you could then save this to file, and then you could view it in your favorite external viewer. And this would be exactly the same. Obviously here it's trivial, we're working with circles, but if this were a brain or if this were in 3D, all of this should apply. One thing that it is worth noting is that our image is generally continuous data, and our labels tend to be categories, so they tend to be discrete steps. When we do the inverse of our outputted inferred segmentation, we will probably want to use nearest neighbor interpolation. So in the forward direction, we'll probably use something like, bilinear, and then in inverse, we'll want to use nearest neighbor. And this is what inverted will do by default. You can disable that if you'd like, but by default, when you do the inverse, it's going to do nearest neighbor because it assumes that most of the time people are interested in doing this for segmentation purposes. So that's it. Hopefully that makes sense. And hopefully if you want to do the inverse transformation of some sort of segmentation, all you should need to do is stick this bit into your post transforms. As I say, once you can then do your inverse transformations, you can do things like test time augmentations. And a test time augmentation can help to give a handle on the uncertainty of a network, and it can also help give a handle onto the sensitivity of your network to your random transformations. So what we could do is we could take an image and we could apply some random data augmentation to it, and we could apply that same, we could create clones of that same input image, and we can apply that random data augmentation to it multiple times. So our image will be in multiple different states. We could run each of those through our model, and so we'll have multiple sets of inferred segmentations. We can then apply the inverse transformation to each of those examples, get them all back into the original space, and then once we have them all superposed, we can then do some sort of calculate some sort of metrics to tell us the variability in the results. And so hopefully you can see how this would help you gauge some sort of uncertainty in your network, or the level of dependence of your network to your random data augmentations. And so I've simplified the post transforms. You'll remember in the previous in the previous cell, it was a compose that had activations discrete, and it also had inverted. So I've removed the inverted now, and our post transform is just activation and as discrete. And that's because the class itself will do the inverse transformation for us. Our inferer function is going to take some input image, it's going to put that through the model, and then it's going to put that through our post transforms. So we'll take an image, we'll infer it, and then we'll run it through activations, and then as discrete. That's it. So we're going to create this class called test time augmentations, get some new data, and run that data through our test time augmentation. And it's going to turn us some information. So for example, we're going to do 100 of these instances. So we're going to take one input image, create 100 clones of it, do 100 lots of data augmentations, 100 lots of inference, and then we're going to compute our noise metrics based on those. And so we'll get the mode on a per voxel basis, we'll get the mean on a per voxel basis, standard deviation, and a scalar that's called the volume variation coefficient. And that will give us a handle. I think it's the standard deviation divided by the mean. And so the larger that is, the more variation there was in those 100 different examples. And so if I show you that, again, this was a really simple example. And so our mode and our mean look very easy, but you could hopefully imagine that as this problem gets more complicated, our inference wouldn't be so sure and certain of what it's doing, and so these images start to become useful. As you would expect, towards the edge of the interface between sort of the segmentation classes, where you have the most uncertainty, and that's what's showing up in our standard deviation. And here we've printed the volume variation coefficient, which is pretty small because the network knows what it's doing. There's a small standard deviation. I think if you go to our MONAI tutorials, so GitHub project MONAI/tutorials, if you go to the modules folder, there's a file called inverse transforms and test time augmentation, and it's exactly the same as the one that I've just run you through now, except that it uses brain images. And so here you can see the test time augmentations for those brain images. So here we've got the inputs, here we've got the ground truth segmentations, and then here we've got the mode of the however many examples we used. Here we used 10 examples. So this is the mode of 10 instances of our sort of inferences that have been then put through the inverse transformations, the means, and the standard deviations. And yeah, that's it. So throughout this notebook, I've briefly motivated why you might be interested in using inverse transformations. Hopefully I've shown that it's relatively simple. All you need to do is use dictionary transformations and then just stick that inverted post transform into your chain of post transforms. And then if you want to then save it to file, you should then be able to easily superpose it on top of your original input image and using your favorite external image viewer. And then lastly, once you can do things like inverse transforms, you can do things like test time augmentations, which can help you in some ways understand what's going on in your model a little bit better. Yeah, that's everything I wanted to say on the topic. Okay. Happy to take any questions.
Great, thanks, Richard. There are a few ones. People have been answering them. I think Dong and Eric have been answering, but I'm going to ask a few of them just because we have a few minutes here at the end, and that way in case people haven't seen the actual questions yet. So let me go back up to the top here. Do transformations take care of the metadata as well?
Yes, I think so. Yeah. Because the inverse tends to just use another one of the MONAI transforms. So for example, if in the forward direction you were doing a crop, then in your backwards, you'll be using a pad. If you're changing the spacing of your image, say initially you had voxels of 1 millimeter, and afterwards you want to have voxels that are 2 millimeter. When you do the inverse, we're just going to put the opposite through into the spacing transformation to then put it back in the opposite direction. So anything that it does in the forwards direction, it will then do in the inverse direction. So for example, spacing D does modify the metadata, and so then when you use the inverse of spacing D, which is also spacing D, it will then modify the metadata, and so it should return to how it was. Yeah.
Great. There's two questions that are pretty similar here. So it was, what's the point to transform the test data and perform the predictions using the pre-trained model? An extra level of checking if the model overfits? Kind of wondering why.
Sorry, could you repeat that one?
What's the point to transform the test data and perform the prediction using the pre-trained model?
Yeah, so there's a couple of things there. I think you would want to put your random transformations in if you were going to do something like test time augmentation. You're right, when you come to using your test data, I mean, hopefully you're at the point where, or say you want to deploy your model even, those ones, normally for our test transformations and our validation transformations, you know, we don't really put any of those random data augmentations. It's only really in the training that we would do that. But you still may want to do the inverse of that. So when it comes to deploying your model, say, if you're perfectly happy with it, as, for example, they do in Clara, you'll want to take your image, apply your basic transformations. So you've set up your model so that it deals with voxels of 2 millimeter. You're still then at deploy time or at test time, you're still going to want to downsample it to 2 millimeter. If then afterwards you then want to save it to file, that's when you would then be applying the inverse. So hopefully that makes sense. So obviously in the training, you would be using more random data augmentations, but there's still transformations that would be applied at validation time and at test time. And it may be useful for you to do the inverse of those, particularly if you want to save those images to file.
Yeah. Great. So we have one more question, sort of a two-parter. So one was, someone was asking, what's the importance of having the divisible p-add, that function that you had in here? And then the follow-up was, because I think Eric did answer some of that as far as the rotations, for rotating dimensions as an XY dimensions of the image, and just kind of understanding what you were doing with that transform.
Yeah, sorry if I skipped over that. I think for our, sorry, I'm going to do part two just because I can't remember what part one is already.
Yeah.
The argument to the random rotation, I think, is range X, range Y, and range Z. And so if you want, you can give a single value. And I think then you'll do from negative. So if you did pi, for example, you go from negative pi to plus pi in the X direction. So that's around rotation around the X axis. And I think if you give two values, which is what I did, you'll say, I want you to go from 1 radian to 2 radian. And the reason I did that was because if I did minus 2 radians to plus 2 radians, then it could be a case where it was at 0 radians. And just for the case of this tutorial, that wouldn't be very illuminating. You wouldn't see anything being transformed. So this is a fairly artificial case, but I just wanted to do from 1 radian to 2 radians, so there would always be some sort of forward motion. So that's why. So that's what the argument range X is doing, and that's why I used a fairly probably a set of arguments that you wouldn't really be using in the real world.
Okay, and then we did have one more come in, and I think we have time for that with 2 more minutes. So, is there a method for inverting patch extraction, i.e., stitching the outputs of the model back with the appropriate averaging over overlapping voxels?
No is the answer. But we do have a sliding window inference, and so that would help you to chop up your image into smaller chunks, put that through the model, then stitch it back together on the other side. So hopefully is that the use case that you're thinking of?
They might be able to follow up and chat with you. There was also another one where I think you can answer in chat because they actually have a picture and they ran through your code and they were having some issues as well. But we can kind of do that one offline or in Discord, I think. I think it'll be a little bit easier to answer over there. But yeah, that was great, Richard. Thank you so much. I think we're
no problem.
at the end of questions.
Perfect. Thanks.
Yeah, thank you.